I don't know if it's going to take one or two videos, sort of see as we go. But in this video, or maybe two, what we're going to be talking about is the gambler's fallacy. So far in this unit, what we've looked at are three different interpretations, philosophical interpretations of what a probability is or what probability means. We saw the classical frequentist and the relative frequentist, both of which take probabilities to be frequencies, mathematical models, and likewise we saw the subjectivist interpretation of probabilities, which takes a probability to be a degree of belief, something internal and epistemic rather than purely mathematical. Now, before we get to formalizing and looking at our equations and laws of probability, the logical laws of probability, I wanted to do a video on the way in which probabilistic thinking can get us into trouble and some really important terms that we're going to have to know in order to set the stage for our formalization of inductive logic. The problem that we're going to be talking about in this video or two is the gambler's fallacy. And some of you may have heard of this, some maybe not, but we're going to go through it today. The first thing that I wanted to note is that a lot of the problems, that is like problems you'll see on your quizzes, problems that we'll talk about in these videos and examples involve gambling, which is it's essentially a helpful tool for understanding the problems of inductive reasoning. Insofar as there are games that we play that are constructed as models of risk or probability, and they play nicely with mathematical calculation. So really, the use of gambling, morally here or there, isn't so much what we're interested in, as much as the models of the games that they represent. Insofar as games of chance are bets, and they're rigidly structured and with sort of simple rules and simple odds, they really help to illuminate the underlying probabilities and problems with regard to thinking about chancy or risky situations. Now, the fact that gambling or playing games of chance or bets, making bets, is the mode of much of the examples of inductive logic, it ought to be clear, or at least hopefully it will be clear, that the terms that we learn and the forms of thinking that we cover in this unit are not merely meant to be applied to games of chance, to gambling, but because we live chancy lives where every day, in every moment almost, we're making decisions that are chancy decisions that are based on probabilities and inferences to the best explanation and based on evidence, right? That we ought to be able to see, hopefully again, that our games of chance and the reasoning therein can be bootstrapped out of the simple games, the gambling scenarios, to our everyday thinking. And so again, gambling and games of chance are just small little helpful models for doing this. So we're going to talk a lot about rolling dice, about flipping coins, a little bit about roulette, and I'm terrible at gambling. I've never won money gambling in my life, but I really enjoy the rules and axioms of probability theory, and so that might be its own philosophical problem for another class and another video, another lecture, or whatever. But we're going to be focusing on the axioms that might make one a good gambler if they were able to apply it to gambling, and likewise make one good at practical reasoning if they could apply similar rules of reasoning, inductive reasoning, to their everyday life. And I think this is something that we can do much easier, which is kind of interesting that the examples are so simple, and yet it's the more complex form of inductive thought, not games of chance, but rather all of the everyday decisions that we make, the complex decisions that we make that find themselves far more aided by inductive reasoning, even though we learn inductive reasoning through the simpler but harder to apply to examples of gambling. Anyways, okay, so the gambler's fallacy. So let's say that I'm playing roulette. And for those of you who don't know about this game, it's a wheel, and the wheel spins, and the wheel is broken up into a whole bunch of slices of pie. There's 36, 38. Yeah, there are 38 of these slices. 18 of them are black, 18 are red, and 2 are green. And they're double zeros. And what happens is the roulette dealer spins the wheel and then drops a little metal ball in it. The metal ball spins around the edge of the wheel, and as the wheel slows down, the ball eventually slows down with it and falls into the groove of one of these slices. It will fall into either a black slice, a red slice, or one of the green double zero slices. So we should assume that we're playing in Vegas or wherever, that the wheel is fair, which we'll talk about shortly, fairness. And here's the gambler's fallacy. I know that there's an equal likelihood, there's an equal probability. The probability of the ball that's dropped on the roulette wheel of landing on black is equal to that of it landing on red, right? There's 18 slices of each color. And in this scenario for the gambler's fallacy, let's assume that the last dozen, so last 12 spins, the ball has fallen on black. So here's the inference. The inference is that because the ball has fallen on black 12 times and there's an equal probability of it falling on black and red, that either the next spin is more likely to be red, or that there will be a series of spins that are red. And so what I do is I put money on red. I see that the wheel has been spun 12 times, and 12 times it's come up black. I think, well, of course, red has to come next, right? Or red has to come soon, because the probabilities are equal and things will balance themselves out. And so because I think this, I put money down, and upon putting my money down, I've made an inference, I've made a decision, and I've committed the gambler's fallacy. Now, we're not going to talk about the gambler's fallacy, why it's a fallacy, until the very end of this lecture. There are some important terms that we have to learn first, but that's the scenario that this video, or 2 videos, sort of depends how long we go, is going to investigate. Okay, so the terms that we have to learn. One is fair. What does it mean to be fair? It's fair that the evildoer gets their just desserts, right? They go to jail. They have some sort of punishment for being evil. It's fair that a coin is not weighted to land more often heads than it does tails. It's fair that, I think this is an example in the book, that 2 greedy children have 1 slice of pie left. Right? Cherry pie is my favorite. So 2 greedy children have a slice of cherry pie, and they want to split it, but they're both greedy. They want what's best for them. And so they come up with a fair agreement, right? One greedy child will slice the piece of pie in half, and the other greedy child chooses which slice to take. And this is fair, right? Because both want as much pie as they can get, and so both are going to do what they can to make the scenario as fair as possible. So a bet on an outcome, like roulette, is going to be fair when one outcome is not favored over the other. When the two greedy children cut their slice of pie and choose it, one outcome is not favored over the other because they're going to try to cut it as equally as possible. Likewise, for the fair coin, one outcome, heads or tails, just so long as the coin isn't weighted, the coin will be fair when there's not a higher likelihood of heads landing than tails or vice versa. The next term that we should know is bias. So bias is something like the weight that makes some outcome more or less likely. So if we loaded a dice, or if we put some weight or constructed a weird looking coin so that it like always flipped heads, or like 60% of the time flipped heads. Likewise, for the weighted dice, you could load more plastic or a little piece of metal on the inside of the dice so that it more often rolls a 1 or something like that, right? And this is a bias. So a bias is a chance setup. A bias is something that determines an outcome to a higher degree than any other outcome, or likewise underdetermines an outcome over any other outcome. So a chance setup, like a fair coin or a roulette wheel that doesn't have magnets that's pulling the ball towards the green zeros or whatever, a chance setup is unbiased if and only if the relative frequency in the long run of each outcome is equal to that of any other. And so what I've done is I've imported a bit of language from one of our earlier theories of probability, right? I've used the term relative frequency. So what we're doing with bias is assuming that we can measure the relative frequency as we observe. So in the long run, if I were to run an infinite number of tests for, say, this roulette wheel, if in that infinite number of tests, like 60, 70, 80% of the time, it landed on the double greens, then I would say that the roulette wheel is not unbiased, that it is in fact biased towards the greens. And the reason that I use an infinite set of tests is because that's the maximally, it's the maximal amount of tests that can be run, so we can be like completely sure that in an infinite series, the roulette wheel is unbiased. And we can become more confident. We can have a higher degree of belief, right? Thinking about that version of probability interpretation. That the roulette wheel is unbiased in an infinite set. And then the lower number of iterations we go down from infinity, the lower our degree of belief will be. But that's sort of an interesting side note, I think. What we should keep in mind, however, is that bias is just a weight towards one outcome over another, or against a particular outcome. And in a chance setup will be unbiased when its relative frequency doesn't favor any particular outcome. So we should note that bias only has to do with the setup of our game of chance. For instance, our roulette wheel, or our dice. I play lots of Dungeons and Dragons. And in Dungeons and Dragons, you're often rolling dice. And these dice are fair. That in a purely random scenario, if you shake and shake and shake without looking and then release, that the dice will be unbiased. That they're not weighted in any particular way, that every outcome, just in virtue of the dice, no outcome is favored over another. They're unbiased dice. However, I might be a biased player. I might cheat, right? I might look at my dice or put the dice in my hand in a particular sort of way so as to roll it so that I'm more likely to get the outcome that I want. Like if I want to roll a 6 on a six-sided dice, I could train myself to hold the dice in a particular way, to appear as if I'm throwing it randomly and then releasing it from my hand with just the same amount of force in just the same sort of way on an exactly flat surface and roll a 6 most of the time. I could train myself to do this. And so even though the dice itself is unbiased, I'm not. And so what we get is an unbiased dice, but an unfair game. That there's a chancy setup, but it's not fair. And so an unbiased game setup might still be unfair. And there's other examples of this. For instance, if, a chess grandmaster is playing against someone who's just learned the rules, right? The game itself is unbiased, right? Because at the beginning, at T0, at the first time, at the first move, the grandmaster's chance of winning is equal to that of the first time player, because the neither will cheat, both of them will follow the rules, and they both have equal setups on their board. Now this is a side note, it's not exactly true because white has slightly more chance of winning because it goes first. But that aside, the grandmaster or first time player distinction creates, even though the board itself is unbiased, an unfairness in the game itself. Okay, so what we want in a true game of chance, and a game of chance that is not simply biased, but is also fair, so we want fair and unbiased, is what we call independence. And here's our definition of independence. Trials on a chance setup, like our roulette wheel, like our rolling the dice, like our flipping the coin, are independent. So trials on a chance setup are independent if and only if the probabilities of the outcomes are not influenced by the outcomes of previous trials. And this is important. Independence. So a game of chance is independent when every iteration, every spin of the roulette wheel, or every roll of the dice is unaffected by any previous or future roll of the dice or spin of the wheel. That I can't make the dice game unfair by learning how to roll them in a particular way, by rolling unbiased dice in a biased way. Rather, every roll of the dice is itself random and disconnected, importantly independent from every other roll of the dice or every other spin of the roulette wheel. And when we think about independence of outcomes, certain words come to mind. We think of randomness, right? That every roll of the die is purely random, that every spin of the wheel is purely random. We think of a no regularity factor, not cheating, right? There's not a regularity in the way in which I roll the dice, or a way in which the wheel is spun, or how the ball is dropped into the roulette wheel. We think of there being no influence on the game, that the grandmaster can't play mind games with the first time player and sort of control her actions in important sorts of ways that would cause her to lose even worse. Or that there's no memory between tests, between iterations, that in the relative frequency leading to infinity, right, of iterations of the roulette wheel, that each iteration itself is measured independently of all the rest, insofar as none of them can see or remember or have any sort of like causal connection with any of the other spins. And so this is our idea of independence. When a game of chance is independent and unbiased, then it is purely fair, right? Because there's no connection between any particular play of the game. And likewise, the game itself is unbiased. There's no favoring of particular outcomes. And so we call these games fair. Now, we can lose one of these and have an unfair game. So we can have unfairness in a couple of different ways. We can have unbiased. and dependent, we can have biased and independent. And finally, we can have biased independent. So a dependent is just the opposite of independence, right? It's when the tests do have some sort of non-chanciness, non-randomness, when I'm able to control the way in which I throw the dice, right? And then bias and unbiased, right, is the opposite of bias. So I've written down some examples. So here's an example of a fair game. So imagine that I have a jar, an urn. I don't know what it is about these textbooks and urns, but the urn is the example that's always used. So here we go. There's an urn, a giant jug, and inside of the urn there are 50 balls. 25 of these balls are blue and 25 of them are red. So the probability before I pull any balls is of pulling a blue ball is going to be 50%. And so each time I pull one, I pull it out and say I get a red one, right? And then the next time I pull a blue one, and the third time, whatever, this is the game, right? And before any of the objects are removed from the urn, there is a 50-50 chance that the color of the object will be blue. And because there's an equal number of the colors of the balls in the urn, we would call this game unbiased, right? Because no outcome is favored over the other. That the outcome pulling a red ball is probabilistically equal to the likelihood of pulling a blue ball. Okay? And now imagine every time I pull one of these balls, I put it back after I see it. So every test resets. That there's always, at every pull, still 50 balls, and still, likewise, an equal probability that I pull a red or a blue in any given test because I'm replacing. And so because I replace and I don't change the test and say like I shake the urn to whatever to mix the balls up, my test is independent. So or my game is independent. So no particular pulling of an object from the urn will affect any future pulling of an object from the urn because I always replace. And so in this game, there's always a 50-50 chance that I pull a blue-colored ball, and every test is independent of every other test because I've replaced it. And so this would be a fair game, much like a fair coin. However, let's say I have, what's my next example? Biased and independent. So this one, biased and independent. A game can be biased and independent. For example, when we roll bones. So an old, very old-timey game, one of the very first games of chance that we're familiar with is that people would take the bones, the knuckle bones, or the vertebra of animals or people, and roll them. And they would color certain sides, and they would bet what color would land when they rolled the bones. It's very much like dice, except the test is biased, but it is independent. Every time you roll the bones doesn't change the way that the future rolls will go. And so there's no connection between any of the rolls, and thus they're independent. However, bones are not uniform surfaces, right? They're unique to the thing that grew them. And so there's going to be a bias in the way that they roll. There's, given the awkward skewed shape of the vertebra or knuckle or whatever, you're going to have certain sides of the bone that are more likely to land face up. And because some outcomes, given the wonky shape, are favored over others, the game is biased. And so even though there's an independence to each role in particular. The game is biased, and thus we would call it, given these definitions, unfair. Likewise, we can have biased and dependent. A game that's biased and let's do actually unbiased and not independent. So the opposite. So our last one was biased but independent. Let's do dependent but unbiased. So that would be this guy. So a game that's unbiased but dependent would be, recall the urn example, right? I'm pulling red and blue balls from the urn. In the original example, that was a fair game using these definitions. We had independence because we replaced the balls, and we had no bias because there was an equal number. So there's 50 balls, 25 of them blue, 25 red, right? Now, in a game that's dependent but unbiased, there's no favoring of one outcome over the other, and yet every time I pull a ball, this time I don't replace them. I set them down to the side. So my urn is here. I pull a ball. I look at its color. I set it down. I pull the next one. I put it down. This game is unbiased because there's no favorable outcomes given the setup of the game. However, it's dependent because the probabilities will change over time given what colors I pull out because I'm not putting them back. And so each pull of a ball from the urn is dependent on any of the previous pulls because it's going to change the number of red, the ratio of red balls to blue balls that are present in the urn. And so this game would also be, on this definition, unfair. Now, our last one, a game that's both biased and dependent, might be halfway through that urn game, right? That I put 90 red balls in an urn and 10 blue ones, and I'm not replacing. And so there's a much higher likelihood that I draw a red ball than I draw a blue one. And I'm not replacing, so I don't get independence. So there's both a favoring of outcome towards red, and I'm not replacing. So there's a dependence of probability on the previous pulls, that the tests are not independent of one another. Okay, so now we've covered independence, dependence, bias, unbiased, and fairness. And because with these new definitions in our philosophical tool belt, we can understand why the gambler's fallacy that we began this video with is a fallacy. And it's a fallacy for the following reason. So what I've done is I've formalized an argument here that the gambler makes. The gambler says, one, the roulette wheel is fair, right? That this is the assumption, that the gambler has gone to Vegas and assumes that this roulette wheel is going to be fair because it's run by, a big casino, and they couldn't get away with sticking magnets in their roulette wheels. But two, the roulette wheel is spun black 12 times. And three, because the game is fair, then the red and the black spins, of course, will occur with equal frequency. Therefore, the gambler concludes, red will come up soon, or a series of red will come up soon, and thus make the frequencies balance themselves out. Therefore, I ought to bet on red occurring, because black has happened a dozen times. Now, this is a fallacy, because the gambler's premises are inconsistent. The gambler assumes fairness, but doesn't assume independence. What the gambler does is say that bias or unbiased is sufficient for fairness. But as we've seen from our urn examples, that fairness requires both unbiased and independent setups. And so, for the reasoning to be sound, we would need to say, one, the setup is fair, and the gambler admits this. And two, there have been 12 blacks, and the inference is that a red will come up soon, but this inference wouldn't be licensed if the roulette wheel were independent, right? Because remember that independence requires that each spin or each test, every iteration of the game of chance, doesn't have any causal relation, connection to any other previous or future one, that it's independent. And so by assuming fairness, we need, again, both unbiased and independence. And so when we spin the wheel, even if there have been 12 black in a row, we're not licensed to say that a red will come up soon. And that's because each test is independent. That it's only on it's only in the single iteration of each test that we're licensed to say there's an equal likelihood that black will appear or that red will appear. But over a period of time, we can't make that inference that because black has come up more often, a red will come up soon. That's not the case because each spin of the wheel is independent of the other. And so inferring from a series that the next in a series will accord with some frequency in a fair game of chance is a fallacy. Yeah, so don't commit the gambler's fallacy. If you go to Vegas and you see that roulette has come up, if you're playing roulette and black has come up a dozen times, don't start betting red because you'll lose money, right? That your best bet is just to go with your gut, right? What feels right? Should I bet black or should I bet red? Because every spin of the wheel is just as likely to turn up black as it is red. And to think otherwise commits the gambler's fallacy because the game is fair, unbiased, and independent. Awesome.